Welcome to G Fun Facts Online. Have you ever stopped to think about thinking? Specifically, how does a fleeting, abstract idea, a feeling of love, a concept like justice, or just the simple desire for a cup of tea, transform into a clear, well-formed sentence? The gap between a silent thought and spoken words is one the human brain crosses in literal milliseconds. It's a feat so complex, it's like a high-wire act of neural choreography. Today, we're pulling back the curtain on this incredible process, exploring the journey from abstract thought to eloquent speech. This isn't magic, it's the dazzling work of your brain's linguistic orchestra. Let's start with the blueprint. Before we can map this process in the brain, we need a cognitive roadmap. Think of it like a factory assembly line for sentences. The most influential model comes from a psycholinguist named Willem Levelt, who proposed a step-by-step process. The first stage is called conceptualization. This is the pre-verbal birth of an idea. Imagine you see a dog chasing a ball. Before any words are formed, your brain creates a mental representation of this event. The dog, the ball, the action of chasing. You decide what you want to communicate. This is the purely conceptual phase. The second stage is formulation, and this is where thought truly meets language. This stage is a critical bridge, and it's broken down into two smaller steps. First is lexical selection. Your brain dips into its vast mental dictionary to pick the right words, or what scientists call lemmas. A lemma is like a word's ID card. It contains its meaning and its grammatical information, like whether it's a noun or a verb, but not its sound yet. So your concept of a furry four-legged friend activates the lemma for dog. After selecting the words dog, chase, and ball, the second step of formulation kicks in, syntactic encoding. Here, the chosen words are arranged into a proper grammatical structure. Your brain builds the frame. The dog is chasing the ball. This is a highly automated process that we do without even thinking. The third and final stage is articulation. The grammatical plan is now converted into a series of muscle commands sent to your tongue, lips, and larynx to produce the actual sounds of speech. And while all this is happening, there's a crucial feedback loop running. Your brain is constantly monitoring your own internal and overt speech, a tiny quality control manager catching and correcting errors on the fly. While Levelt's assembly line is a great model, some scientists, like Ray Jackendoff, propose a more cooperative system. In his view, the sound, grammar, and meaning of a sentence are all being built at the same time, in parallel, constantly influencing each other. It's less like a line and more like a team of builders working on different parts of a house simultaneously. So with this blueprint in mind, where in the brain does this all happen? The journey begins in the prefrontal cortex, or PFC, the brain's executive control center located right behind your forehead. The PFC is responsible for planning, decision-making, and crucially, handling abstract thoughts, ideas that don't have a direct physical form. MIT researchers found that the PFC is where the brain processes concepts like same or different. It's the CEO of your brain, forming the initial communicative intention. This pre-verbal message is then sent to the language specialists. You've likely heard of the two most famous players, Broca's area and Wernicke's area, both typically located in the brain's left hemisphere. Broca's area, situated in the left frontal lobe, is the production manager and grammar architect. It's essential for putting words into grammatically correct sentences and planning the motor movements of speech. If this area is damaged, a person develops Broca's aphasia. They can understand language, but they struggle to produce fluent grammatical speech. Their sentences are often slow, effortful, and missing small connecting words. Then there's Wernicke's area, located in the temporal lobe. Think of this as the brain's master dictionary and comprehension center. It's where language is processed and infused with meaning. Damage to this region leads to Wernicke's aphasia. Individuals can speak fluently and grammatically, but their speech is often a nonsensical word salad, devoid of meaning. They also have immense difficulty understanding what others are saying. These two areas are connected by a massive bundle of nerve fibers called the arcuate fasciculus, a neural superhighway that allows for the smooth flow of information between understanding and producing language. Now, this classic model is a great start, but modern brain imaging has revealed a more nuanced picture. Today, the leading theory is the dual-stream model. Imagine two distinct pathways leading out from the parts of your brain that process sound. The first is the dorsal stream, often called the how pathway. It connects the temporal lobe to the frontal lobe, including Broca's area. This stream is responsible for mapping sounds to articulation. It's crucial for speech production, repeating what you hear, and processing complex grammar. The second is the ventral stream, or the what pathway. This connects different parts of the temporal lobe and is primarily responsible for mapping sound to meaning. It's your comprehension pathway. So producing a sentence isn't just a simple handoff from Wernicke's to Broca's area. It's a parallel process using two interacting networks. And none of this would be possible without working memory, the brain's mental sketchpad. As you build a sentence, you have to hold the overall message in your mind while you select words and arrange them. Your working memory capacity is a critical resource, managed heavily by the prefrontal cortex, that allows this complex construction to happen without falling apart. Now, if the brain regions are the sections of our linguistic orchestra, what keeps them all playing in time? The answer is neural oscillations, more commonly known as brain waves. These rhythmic electrical pulses, generated by large groups of neurons firing together, are the conductor's tempo, ensuring every part of the network is perfectly synchronized. Different frequencies are linked to different jobs. Theta waves, which are slow rhythms vibrating between 4 and 8 times per second, are deeply involved in memory access and retrieving words from your mental dictionary. They also seem to help organize language, chunking a sentence into meaningful phrases. Then you have the much faster gamma waves, vibrating at over 30 times per second. These are thought to be the binding waves. They act like neural glue, integrating the different features of a word, like its sound and its meaning, into a single unified concept. It's this beautiful, intricate dance between different brain rhythms, what scientists call cross-frequency coupling, that allows the whole system to be coordinated with millisecond precision. A slow theta wave might parse a sentence into clauses, while the faster gamma waves within each theta cycle bind the features of the individual words. Here's a mind-bending question. Does the language you speak actually shape how you think? This idea is called linguistic relativity, and neuroscience is starting to show that it's true. Studies have found that grammatical features in a language can subtly influence how speakers perceive the world. For instance, in languages like German or Spanish, where nouns have a grammatical gender, speakers might unconsciously associate masculine or feminine qualities with those objects, even if they're inanimate. Your brain's conceptual filing system is literally tuned by your linguistic and cultural experiences. We've also gained profound insights into this system by studying what happens when it breaks down. Aphasia, a language disorder resulting from brain damage like a stroke, can cause very specific problems that illuminate the different stages of production. As we mentioned, damage to Broca's area shows us its role in grammar and production, while damage to Wernicke's area highlights its role in meaning. There's another type, called anomic aphasia, which is characterized by a primary difficulty in word finding. A person with anomia might know exactly what they want to say. They can describe an object in detail, but they simply cannot retrieve the name for it. This shows us that the lexical selection step, mapping a concept to its word, is a distinct and fragile part of the process. This brings us to the future, which is happening right now. The field is being revolutionized by artificial intelligence. In incredible new studies, researchers are using AI to decode language directly from brain signals. By training models on the brain activity of people reading, or even just thinking about sentences, they can reconstruct the words directly from non-invasive EEG recordings. They are literally beginning to crack the neural code of language, watching the cascade from abstract idea to specific words unfold in the brain's electrical activity. This not only offers a deeper understanding of our own minds, but also paves the way for advanced brain-computer interfaces that could one day restore the gift of communication to those who have lost it. So the journey from thought to speech is a symphony of breathtaking complexity. It begins with an abstract spark in the executive suite of the prefrontal cortex. This idea is then sent to a network of specialists in the temporal and frontal lobes, where it's dressed in words and grammar according to a cognitive blueprint. All the while, an orchestra of neural oscillations ensures every element is perfectly timed and integrated. The next time you effortlessly share a thought, ask a question, or tell a story, take a moment to appreciate the silent, intricate, and absolutely profound performance happening inside your head. Thank you for listening to G Fun Facts Online.